Okay, so welcome everybody to another session of the seminar series on diffusion modeling and timescales that we've been running here today. And we have two speakers today on slightly different topics. So first we'll have Massimo Pompilio talking about petrological monitoring of active volcanoes and the role of diffusion chronometry in it. And then Euan Mutch would talk about some of the particularities of modeling things in plagioclase. Now, just to get started and to introduce the format to those of you who may not have been here before. So these two talks will be in sequence. So we'll start with the first talk, about half an hour or so, and then we'll have a few questions on that talk. And then we'll go on to the second talk. And then at the end of the second talk, we'll take questions for the second talk as well as the first one. So if your question doesn't get addressed right away, or if you come up with a question later on, please feel free to just have them coming in, and the whole idea is to have enough discussion and not run out of time to discuss and talk about the things. So the other thing I wanted to announce already now is that after this session here today, we'll go on a kind of a summer break, and we'll be back in the fall again in September, October, and we'll announce that so you know. So with that, I think I'll start off by introducing the first speaker, Massimo Pompilio. Massimo has been working on various volcanic things for a very long time and has had a very real life experience of working for an organization where you actually whose job is to monitor volcanoes and to study volcanoes. So he began working at the INGV in Italy in the Catania section in 1989, which is right at the foot of Mount Etna, for those of you who want to locate the place a little bit. And as a result, then and all through, Massimo has worked a lot on different aspects of volcanism in Etna, but also on the efforts that go on to monitoring Etna and other volcanoes. So he moved to the INGV in Pisa in 2004, and he's been there till 2021, and since then he's been a senior scientist at INGV Pisa. Now, Massimo has done a lot of other things during his time. He has spent some time doing experiments at the University of Orleans. He has been on a expedition to Antarctica and has done quite a bit of work on Antarctic samples, and he has organized various workshops and programs within the scope of EU things, including one on called MemoVolc on discussing the different aspects of what a plumbing system of a volcano should be. So in short, Massimo has a very broad background and a lot of experience he brings towards discussing the issue of monitoring, and I would just let him take on. Massimo. So I'll just stop sharing, and so you can, also the title once again is Petrological Monitoring of Active Volcanoes and Diffusion Chronometry, a close relationship for a mutual benefit. Massimo.
Okay, thank you very much, Sumit, and good afternoon to everybody. And also thank you, Sumit, for this opportunity to talk of this. Can you see my presentation?
Yes, you're fine.
Okay. So today we will talk about the pathological monitoring of active volcanoes and some relationship with diffusion chronometry. And I wrote a close relationship for a mutual benefit because both can have a good benefit with the interaction. This talk is based on a recent paper doing a sort of review, assisting procedure to achieve best practice in for petrological monitoring during the eruption. So just to start, a sort of rationale of this talk, one of the main potential of diffusion chronology is that it allows to correlation between time scale of magmatic processes inferred from petrological data and also from real-time monitoring signal. But to do this, the diffusion chronology needs also the samples that are well constrained on the point of view of the time. And one of the tasks of petrological monitor is to collect and investigate samples among which the time relationship are known unequivocally or with some error. But just to have an idea, you can see here, this is a diagram from a paper that I co-authored with Sumit and Maren Cole and Fidel Costa. You can see here the time scale record obtained from modeling the diffusive modification in olivine. The more than 65% is within time scale within the few 30 days, 1 month. So if you have a bad constraint about the time, you can have also bad constraint about this time scale. You can see the same things here. You can see, for example, that the most of a mixing period occur few days with time scale of a few days. So if you have a bad determination of the time of the eruption, all this doesn't work very well. So what about the volcano monitoring? Volcano monitoring is generally commonly performed to a real-time acquisition of seismic, geodetic, gas geochemistry signals, mostly acquired by instrumental networks. And obviously, these signals can indicate change in magmatic system before doing an eruption, and so we are able to track magma migration toward the surface. You can see here the INGV monitoring network in Sicily. This is the Etna, with different kind of sensors. These are the Aeolian Island, and this is Stromboli, for example. There are a lot of stations. However, geophysicists in general doesn't see the magma. None of the above-mentioned systems allow a direct view of the magma itself. On the other hand, the petrological monitoring focuses on solid volcanic processes. So take a sort of piece of magma that arrives on the surface, and it's all the petrological monitoring is aimed at understanding the history of the magma in terms of storage zone, transport pathway, and time scale of magmatic process. So this is the more important thing. Tracking the variation of magma properties during the course of the eruption. If we integrate the petrological data, real-time signal obtained by instrumental method, this integration can enhance our volcano monitoring capability, linking what is become before the eruption from what arrived in surveys. Some definition, what is the petrological monitoring? As I said, this focus on solid erupted products of volcanic activities in order to assess the natural magma, architectural plumbing system, mechanism of magma supply, the related action dynamics, and also eruptive processing. For example, if mechanism of fragmentation, if you have an interaction with water or brittle fragmentation or different kind of eruptive process. However, one of the problems is that the petrological monitoring require that an eruption is ongoing. We can see that after that sometimes we can assume also different things. We need also that solid volcanic products are erupted that can be collected. This is another problem. And another important thing is that petrological analysis and interpretation are accomplished during syneruptive phases. On the right, you can see a typical product of petrological monitoring. This is Piton de la Fournaise. Is a paper of Alain Peltier et al. Of 2009. You can see some volcanological parameter here, volume and composition of rocks, in particular potassium and magnesium, calcium, aluminium, and the results is also the interpretation of the magma movement within the plumbing system of the volcano. This is a typical aspect. Another important definition is that petrological monitoring has two ways of action. A scenario study, which is carried out during the volcanic crisis, and has also immediate benefit for the monitoring framework. You can discuss with your colleague and you can have immediately. The other thing is that you have an extended petrological study that expand all the data set that you collected during the eruption and generally take additional time and seeks to place constraint on some specific feature of the magmatic processes. Sometimes also the eruption lasts for a long time, so you have enough time to do this, also to understand better what is going on. I would like to do also a sort of historical perspective, because the petrological monitoring is a sort of history, obviously, of research on this topic, but is also a sort of history of technical advancement that allowed more to collect more data, more precise data, and also the data in more quickly in some way. So in general, the first scientific, to my knowledge, but the first scientific paper giving an account of petrological monitoring is the report of Wilcox on the products of the long eruption of Paricutin from 1943 to 1952. But the first systematic sampling was carried out by Murat and Richter during the eruption 1959 in Kilauea. And in the paper, it's nice to read that there are special advantages in studying fresh pumice and lava collected near the vent during an eruption. The time relationship where the sample is low without problem, weathering is low, and petrochemical data can be correlated with temperature and other geophysical variable measured during the eruption. And so this is the base of the petrological monitoring. And you can see here the diagram for the Paricutin. You can see on the right, this is the chemical composition. On the right, there is also the petrographical observation. In particular, this is the modal content of different minerals or different phenocrysts, and also the mineral content, the abundance of minerals within the ground mass, but during the time. In general, the author described also the sampling procedure. The sampling is a delicate question for the petrological monitoring. They use the same method that we use now. So we spread a large piece of canvas on the ground downwind of the vent to collect pumice or cinder produced by lava fountains from summit craters twice per day. This is important, also the periodicity. Lava flow can be sampled from the vents, if possible, or along the fissure during the flank eruption. In order to have an idea also of the composition, they analyzed only the silica, because in that period it was impossible to analyze. All the methods for analysis was by wet methods. So the silica can give also an idea of what is the composition. But all the analysis was done subsequently in the laboratory of USGS, not in Hawaii. So anticipating what is the modern petrological monitoring organization. After this first attempt, there are, from 1970 to 1990, several eruptions in which petrological monitoring was applied. One is the long-lived Kilauea eruption that started in 1984 in Mauna Loa. Other eruptions like Etna, Piton de la Fournaise, Arenal, Colima, and other active volcanoes. In general, petrological monitoring became a precious source of information to understand the processes of magma generation, sand differentiation, mixing, and so on. But this was possible because there was the development of rapid multi-element analysis like XRF, and also the first microbeam analytical techniques, for example, the microprobe, CMDS. So the people was also able to obtain chemical analysis of bark rock, glasses, and individual mineral files in a short time. This is critical during the CNRT monitoring. You can see here, for example, the content of crystal during the eruption, 1983 eruption of Etna. This is the crystallinity, for example, increase from the beginning to the end. And this is also the Kilauea magnesium content from the 1984 to 2012, and the correlated magnesium gas thermometry. This is temperature in red. You can see below also all the chemical variation in products of Kilauea from the beginning of the past century to 2010. It's okay, let me know. I don't have a feedback of you, so I don't know if it's okay or...
It's very good, Massimo.
After this, in 1980, during the Mount St. Helens, there was also the opportunity to apply petrological monitoring techniques also to more evolved silica system, like that Mount St. Helens produces the big Plinian eruption in May of 1980. As in particular, also the activity that followed the climatic eruption, for example, the growing lava dome, was followed by a team that did a sort of regular sampling over time. Sampling a dome is not like sampling a lava flow. I will show after what are the... And in general, the petrological monitoring were also applied to dome extraction, also in other explosive eruptions like Mount Redoubt, or during the 1990s, also the evolution of the Sophia Hill volcano. You can see some diagram here with the crystallinity or silica content. This is after the same things and same composition against time. Here on the right is from a paper from Devine, in which they evaluated the action rate on the basis of the thin-rimmed amphibole, and on the basis of the thickness of the rim, in order to have an estimate of action trace on the basis of this. Since the late 1980s, the further development of microanalytical techniques like the FTIR or SIMS allowed also to do an evaluation of water, of general, of volatile content inside the mineral, within the ore environment, and so on. This is the paper for Cerro Negro, the Roggensack, in which they estimated the content of water in melt inclusion, and they also did a sort of evolution during the time. A similar paper for the eruption of 2002 of the chronometry, in which she estimated also the pressure of re-equilibration of melt inclusion, so that we think also the pressure of the storage of this system before the eruption. It's the first time that this is done on it. Another improvement is that later in 1980, the application of digital image analysis to textual analysis of radioactive products. And on this, we are able to have quantitative data on crystal and vesicle distribution in the magma. On the basis of this quantitative approach, following different methods, we estimated time scale of the magma storage, the gas fragmentation before the eruption. This is the case of the Etna, in which the analysis of olivine and plagioclase give a different, for the first time, the time scale of crystallization before the eruption is about 3 years for olivine and 1.5 years for plagioclase. The similar things with different assumption. If you have considered xenocrust, or you consider xenocrust, but it's about more than the near for the storage time. This is for the eruption in 1959 from Mangan et al. And this is also for the first time the vesicle state distribution estimated on the basis of a quantitative territorial approach. Now it's very easy to do this because in the digital era it's very easy, it's very fast also, but in the past it was not so easy. Another important thing is that sometimes the scenario monitoring becomes really critical. In particular, as Stromboli, the immediate collection of sample after a paroxysmal eruption, just immediately after, allowed also to recognize two different kinds of magma. One magma, which is black, like black scoria, here is black scoria, BS, black scoria in this diagram. And another, which is called the pumiceous bomb, this here, or also golden pumice. And these two magma normally are eruted only during the paroxysm. And this also, for the first time, the people was able to recognize the role of this deep, rich magma and during as trigger of the paroxysm. There are a lot of studies after this in the following year. Now there are big discussion, very sophisticated discussion if this, what is the trigger of if the dominant the shell of dynamics of magma, or is more important like trigger the deep part. But just to have an idea that without without the petrological monitor, this was not a systematic petrological. This was not possible. I go very fast. Another thing very important. The case one was AFL in 2010, in which immediately just the people, the scientists who were involved in this, realized that there are two different systems, one with a basaltic that appeared at the beginning of the eruption, and one with a different composition in the second phase of the eruption. The same things on Etna for the eruption 2001, in which the upper vent, the lower vent, in the southern part of the volcano produced magma with different crystallinity. This is the upper vent, typical rocks, and different crystallinity, also different composition. And this obviously was interpreted with a different action path from the different fissure system. I go very fast. The scenario plus the extended monitoring allowed also to do several studies. For example, during the eruption of El Hierro, the scenario allowed to recognize that there was, to explain the presence of this white rhyolitic or trachytic rocks within the basalts. Some people, particularly thought that interpreted this like a contamination or assimilation of sediments at the base of the volcano. Other people interpret in different way, but I don't want to discuss about this. But just to see that after this, during the eruption, there was also the application to try to explain immediately, to do a sort of first hypothesis of how is the architecture of the plumbing system. This is the paper of Marty. Longbray also did a similar thing, also doing some integration with the seismic data, and also with for the first time also with the diffusion chronometry on olivine. Another thing that is important here, I would like to show these are similar things with Marty, with composition, as the difference between the bulk rock, which is in which the calcium aluminum or the magnesium increase, and the glass which remain constant. So this is the first time, for my opinion, in which there are differences. This is due, obviously, to the cumulative part of the bulk rock. And this, for me, convinced me that the bulk rock can have problems for doing this kind of work. But it's useful to have both analysis, glass and bulk rock, in order to have more information. I go very quickly. Another things that volcanic products can be used for the monitoring is the ash. Ash is more easy because you have easy to collect, sometimes arrive on your head or your car or on the roof and so on. So it's very easy to understand, but sometimes it's also a big problem. I will show now two different rapidly two different cases, in which one is in Etna 2001, in which we measured the different components of the hash during the time. You can see here that the tachylite, which is the more crystallized part, together with felsic crystals, are dominant during the first phase of the eruption, when the eruption was hydromagmatic. When the eruption starts to be strombolian and very violent strombolian in some cases, the fresh glass or clean glass, the sideromelan, was dominant. At the end of the eruption, with the formation of a sort of plug in the conduit, the more crystallized part was dominant. A similar thing was also studied for the Tungurahua, in which the authors associated the crystallinity to the ascent rate, to the decompression rate. Another important thing in story is the precursory activity. Sometimes, in particular, when you have an arrest of volcano which is dormant, for example, the Mount St. Helens, even during maybe the phreatic or phreatomagmatic activity, you can have also some piece of the fresh magma. The problem is to recognize this. For example, Cashman and Doblit recognized it only after 2 decades that some juvenile material was probably involved in most of the ash-bearing explosion at Mount St. Helens during the precursory period. And this is the image of the part. You can see the bubble here. This is typical of magma, not the gas, not totally crystallized like a lava or like a dome. Similar thing was observed from Schiavi et al. At Netzer Stromboli during the resumption of the explosive activity after the collapse of the crater floor in 2003. One of the problems during the precursor activity is that the complexity to identify fresh juvenile material. And recently there appeared a paper on best practice in which there are some advice on how to do what is the right grain size to do this, but it's not easy. For example, the presence of the absence of juvenile clast in ash emitted during the phreatic activity conditioned a very violent and political discussion and also scientific during the arrest of 1970. You can see here the discussion between Allegre and Tazieff that were in two different positions respect to the presence of the fresh material. But on the basis of this, there was also the evacuation of more than of all the town in the island. More recently, during the ash erupted during the phreatic activity of Temari, the authors told you that sometimes it's not really easy, that sometimes it's very not the ability to identify only under light microscopy of the same juvenile pyroclast is not easy, it's very hard. Because sometimes this part belongs to or material which is recycled, or some material which is mechanically breaked, but not as can happen during a phreatic eruption, but without the involvement of fresh magma. One of the possible solution is to see the composition. If the composition, if we assume that the fresh magma will have a very homogeneous composition. If you have all the composition of the same volcano from basalt to rhyolite in the same ash, probably the material is not fresh. So in general, just to arrive to what is the work done recently, in general, the petrological monitoring reached in the recent time a very mature stage because it can also rely on sophisticated advanced analytical techniques. And but to improve this, in order to have also an integration with other disciplines, we tried to define a sort of best practice protocol in order to have also a good interaction with the other monitoring discipline. There are a large number of worldwide institutions dealing with petrological monitoring. We tried to send, using the VOVO, which is the IRC organization of volcanoes observatory in the world, to do in the framework of Aero Work project. We did a sort of survey. We sent this survey to several institutions, but only 20% answered. The critical part that was absent a contribution from East and Southeast Asian province, for example, Indonesia, Philippines, Japan, that have a lot of volcanoes, and also Russia, in which there are also very dangerous volcanoes. However, we can consider also this sample of the institution doing a very good, very representative, because we have a large spectrum of magma composition, eruptive style, and so we think that what we got is representative of what. So the aim is to define the most common techniques adopted, to highlight the most critical issues that affect the fast achievement of the result that can be used for monitoring, and to rate the possibility of specific investigation in terms of cost and benefits, time of resource versus value of the primary result. The final aims are also to assess the minimum requirement to perform a good petrological monitoring during the ongoing eruption, and to suggest the best practice and operative protocol as useful guideline for all the world monitoring institutions. So the main elements of the surveys are staff organization, sampling strategies, where, how often, for lava pyroclast, sample preparation, where, how, laboratory analysis, data elaboration, results, interpretation, and dissemination. The first part is staff organization. Most of the institutions have a dedicated staff, in average 5 people. Most of the people are on duty for the field work. We divided for if people are doing the laboratory or field work. Sometimes the same people do the same. When I was in Catania, I did the same. So I went there to collect the sample, but I also managed a laboratory for doing analysis. Another problem is the time of forward before an eruption. Usually, the dedicated staff require less than 24 hours of forward. We can see now different aspects. For example, the sampling techniques. For example, the lava can be sampled close to the vent. You can see here different bend, putting the rod inside the lava, or along the channel lava flow, or along the front. There are different kinds. It's much more complicated in case of lava dome, in which it's impossible to approach the lava dome because the danger of explosion. Sometimes, for example, this is some tenants. In some tenants, the people arrived to land here, SH, for a short time to collect a sample. But after that, they try to sample with a dredge. from the helicopter. You can see this. Grabbing the rocks from the side of the dome. One of the problems, in my opinion, of this is this sample represent the magma that was erupted in that day, or is a magma that stayed there for several days and so on. This is one of the problems. The representativeness of the sample, but it's the only way. So, or in this way, or no way. Just to comment some 12 institutions perform lava sampling. Most lava samples are collected from chilled flow. This means from a cold portion in lava surface of levee, or external cold part of carapace, or only one hot portion of lava flow. The percentage is not 100 because you can have also a multiple answer. Most of the people collect the sample at the front. This is another problem. Sometimes you have a lava flow that can also be 10 kilometers. So at the front is the representative of the magmatic system at the day of the sampling? Probably no. This can be should be considered like a minimum eruption date within a flowing channel at the vent. This is at the vent is the best how do you quench sample in air, water, or snow? What do you collect sample? We dump most of people and metal rod. Only one with Mount Santel and helicopter dredge and sampling device in the channel. Sometimes during the lava sampling, people do also some measurement of other parameters. For example, the temperature. Temperature is more popular. Sometimes the output rate or flow rate or flow front advancement. Some case also viscosity, but it's very rare. How often the lava sampling? Generally, when there are several changes in eruptive style, or opportunistic when the people go there daily, weekly, and so on. But after the volcanic eruption, obviously, if you have a very fast eruption, a very short-living eruption is the only way. Pyroclast the same. Most of people collect the pyroclast on the ground or on the snow. And in the recent year, there was start to be very popular, some automatic sampler rush. This is from Shimano et al. Is a sort of drum with different containers that rotate with a timer and collect different sample in time. Most of people collect, most institutions perform sampling of fallout. Sampling location range from distal to proximal area, depending on the class size. A similar techniques are also used for sampling ash and lapilli. Some people also do sampling of pyroclastic density currents. It is a problem, in particular, the main problem for the PDC is the recognition also here of the juvenile component. Most of people do sort of class picking in order to have to select the juvenile part. Okay, on the basis of this, we try to draw a best practice only for the sampling. So the sampling generally should start soon after the eruption onset, because the possibility to collect the time zero as close to possible to the eruption is crucial in order to have a comparison with the previous eruption and to check if the magmatic system has changed. And the time zero is much more important in case we are monitoring we are doing an arrest of quantity of volcano. We have an idea what will be the composition of the, for example, in this moment in Italy, there are an arrest of a Phlegraean field and also of volcano. And the first activity that produced something that petrologists can sample will give us an idea of what is what is going on. If there is a new phases or is a past phases with the different, or if the magma arrive from the deep or arrive from the shallow part of the plummeting system. Another important thing is to quench is the glassy sample that the sample that should be quenched in order to if we want to focus on magmatic processing. Also, this is particularly important for the diffusion chronology, because if you have several hours to cool the sample, all this you can have also re-equilibration. You have growth of crystal, growth of rim of minerals, and so on. And if possible, the lava should be sampled closer to the vent. The abstraction is good, for example, because it's a sort of snapshot of the magma erupted in that moment. But one of the problems, as I explained before, is that the magma that should represent the juvenile fraction. Another problem is the safety first. For the field work should be well planned, and all the tasks of sampling should be safely and rapidly accomplished. This is very important. The second part is not the talk, so I need 5 or 6 slides more. It's related to laboratory analysis. Where is done the laboratory analysis? We divided depends from which kind of analysis. Most can be done within home institution. Home institution, I mean in the observatory or in a different branch of the same organization. For example, INGV the sampling can be done in Catania, and the sample can be sent to Pisa, Rome, or Naples, and so on, to improve to make more analysis. I know that the same things happen in the USGS. Sometimes you can have a collaboration with the other institution, can be academia or the other research institution, and sometimes people also try to buy analysis, in particular for laser ECPMS or black rock is easy, and there are several commercial companies that do the analysis in a short time with the payment. How fast? Also here we have different situation. Depends from the analysis. We have fast analysis. We consider fast analysis all the analysis with a time frame ranging from hours to few days. Here, this fast analysis are all the analyses that are below this dashed line. So component is fast, class shaper morphology is fast, glass isotope is not fast, mineral isotope are considered not fast, melting inclusion volatile is useful, but is not a fast method, in particular for the preparation of the sample. But crystallinity, petrography, vesicularity, crystal size distribution, and vesicle of glass major element and are considered fast. How important? So how do people perceive our perception of the relevance of each analysis? We try to evaluate this doing a sort of classification from 1 to 5. 5 very important, 1 less important. And we see that the people perceive that more important analyses are the componentry, the lithosedimentology, including componentry, grain size distribution, cluster shape morphology, crystallinity, petrography, vesicularity, and so on. But less important, for example, glass isotope, or even here, mineral isotope. The people think that it's important also to do melt inclusion, and so on. And important diffusion chronology. More than 50% think that diffusive chronology is very important. Okay, if we try to, in order to identify best analytical practice, we can correlate fast and easy analysis in terms of resource, equipment, and time availability with what is the perceived relevance of the result in terms of the knowledge of magmatic system. We did this with this diagram. This is rapidity, and this is the perceived importance. And we were able to distinguish different quadrants, one with fast and highly rate analysis. Most of this is petrographic, crystallinity, vesicularity, that are important but fast. Another kind of analysis that are slow but highly rated for diffusive chronology is here. Melt inclusion is here. Bark rock is here, but glass, for example, is in the fast and the highly rated analysis. Other analyses that are important, for example, vesicle size distribution, crystal size distribution, and bark rock trace elements and mineral trace elements, and other analyses like RSM isotope in ground ones on bark rock that are important but are less important. On the basis of this, we classified the analysis of the methods in 4 different groups: essential, important, complementary, and accessory. Essential analysis should be mandatory for every monitoring institution. This is our thinking, but so we hope that resources for different institutions can be invested in the infrastructure, equipment, and also staff to make this analysis achievable in a short time frame. We also propose here a sort of, on the basis of this, a sort of flow chart of what should be done during eruption for the petrological monitoring. You have the eruption, the sampling, if you have current sample, lava dome, lava bombs, or unconsolidated sample of lapilli flash, and all the things you can follow what you want here. In the color are the same, so we consider this as essential, all the lithosedimentological, textural, major element geochemistry, and so on. You can see here that diffusion chronology, which is here, we cannot put in some place, but because it depends from several analysis. You should have glass matrix, or you should have also trace elements, some case major elements, or minerals, trace element, mineral, melting culture in case you do diffusion of volatile, and so on. So all these black line go to in diffusion chronology. Some final consideration. So in general, after this survey, we registered an increasing perception that petrological investigation consistently improve the volcano monitoring. So there is a more consciousness about this. But we know also that in most observatories, there are the parties are already consolidated, dedicated, and there is a dedicated staff responding in a short time. The major issue for most of the people are logistic difficulties in accomplishing field surveys for sample collection, the inadequacy of on-site infrastructure for sample preparation and analysis, and in particular also the shortage of skilled human resource, people that work there. All these aspects contribute to lengthening the time to undertake petrology monitoring, and this obviously decrease also the possibility to interact with the other discipline. Expectations are the management of monitoring institution those the essential role of the petrology. This is our hope, together with other monitoring disciplines in the operative procedure of senior routine monitoring. This will contribute to implementation of facilities and application standards as a minimum global protocol. So my idea is that the monitoring petrology is not a minor system of monitoring. It's like the other system. The only problem is that we should convince all the people that we can do the same things or the other discipline in a short time in order to contribute. I will finish with some future development. One of the problems is the improvement of frequency safety of the sampling using automatic device or drones, for example, remotely operated vehicle. we also hope that sometimes we can think, so we can conceive some mobile labs that can be also portable high-tech instrumentation. SEM now you can put on a desktop to employ in case of unrest of remote volcanoes or in poorly developed countries of the world. And to use methods that utilize a limited sample preparation short analysis time. For example, X-ray microcomputed tomography that allow to do crystal size and also crystal composition, we hopefully sometime. The use locally of SEM and laser ablation techniques that allow full compositional characterization of glass and mineral in a matter product only after a fast sample preparation approximate. And hope this is also one of the aim of this talk. We hope that in the immediate future, the methods of sample preparation and analytical techniques related to diffusion chronology will be improved and made faster in order to obtain a correlation between time scale of magmatic process and real-time monitor signal. Thank you very much.
Thank you, Massimo. That's a very nice review with a perspective from where it all began to what we have going on now and where we can head in the future. So that spans the whole range. Now, in keeping with the tune of things, I'll see if there are questions immediately for Massimo before we go on to the next talk. So you can either unmute yourself and ask questions or type in something in the chat.
Good afternoon, dear Professor.
Yes, go ahead.
Thank you for that presentation. I have some question, but the first is on the topics. I will say the topics is on, so they have diffusion chronometry in the topics, and I would like to know more what is really diffusion chronometry. Maybe I just saw some part of the presentation, but I would like to know what is exactly the diffusion chronometry.
So you are just I try to share again the. So you're asking if which part of in general, you can use diffusion chronology from using different techniques in general. You can use with the minerals or with the glass and several things. So when I was talking is in general, all the techniques imply any case you have an analysis, the preparation or microanalysis in some case. I don't know any system that in which you collect the sample and you put inside some probe and you analyze in a short time. So I think, if you know, I don't know, but which kind of diffusion chronology you can use? Every kind. You can use disequilibrium without mineral. You can use glass mineral. You can use diffusion without the glass. What you want. But you need to prepare the sample. You need at least some hour. You need to have an analysis with a good resolution, spatial resolution. And you need to interpret this with some models. And if this is the question, I cannot say what. So my talk is about, in general, the category of the diffusion chronology, not about a singular type. Okay.
Does that answer your question, or is your question what is diffusion chronometry?
Yes. If there is something, maybe Professor Massimo can just add again, but some things are clear now.
Mm-hmm.
So this is I have another question.
Yeah, go ahead.
Okay. The other ones is on the petrological monitoring, and in the presentation Okay, I was just waiting that we will say after petrological monitoring, we could say we could just deduce maybe how the eruption are going to be in the next time, but or I don't know, some things like maybe we will just continue to have an effusion eruption or maybe explosive eruption, but I didn't understand about that. And I would like to know what we are doing petrological monitoring. What is the aims? What is the aims? So what do we look when we are doing petrological monitoring? Yes.
Okay. So one of the case, for example, just one, you know that. I will try to show. For example, just to take the example of AFL no, or maybe here, El Hierro, okay? Can you see?
Yes, yes.
El Hierro, during the eruption, the fixed products that were erupted are, in general, trachyte with basalt inside the trachyte. Outside, the external part was basalt, inside was trachyte. So you can imagine, one, that a trachytic magma chamber is reactivated, rejuvenated. So you can expect, for example, a big explosion or big explosive activity, maybe a plenum eruption, I don't know. If this trachyte represents a magma chamber. But if trachyte represents some sediments or a part of assimilated, a part of geothermal system that is altered and so on, and altered by pyrometamorphic and melted and so on, is totally different. The possible scenarios are normal explosive, normally eruption without, in this case is a submarine, but without not a violent eruption, maybe with a lava flow and nothing more. So even on the basis of on the composition, you can have an idea what can be the evolution of the system. The system can change, obviously, but you can have an idea. The same, for example, in AFL, you have at the beginning an activity with basalt, so it can be normal activity, but then after this basalt, you have a more evolved part. So you can imagine that you can have a magma chamber with more evolved composition, with explosivity that is more higher, and so on. So sometimes you have this just looking at the rocks, just looking at in sections. So in less than 1 hour. For example, just to have an idea, the next eruption of Vesuvius. Okay. What is the composition? People don't know in this moment. But maybe there is a phreatic explosion, and we can see a piece of basalts or a piece of a phonolite will be totally different.
Oh, yes.
The forecast. I don't know if it's clear this.
Yeah, so basically you can, if you get a quick sense of what the compositions are, you can begin to anticipate what you might be seeing. So this is something we can continue on, but I think at this point I'll stop this and go to the next talk. Let me just see if I can share screen again.
Okay.
So, so the next speaker is Euan Mutch from the Lamont-Doherty Observatory in Colombia. Now, Euan did his PhD in Cambridge, where he came from Bristol to work on his PhD. So for his master's, he had already worked on something that's actually also related to the kinds of things we discuss here, barometry using amphiboles with John Blundy in Bristol. He followed that up with a PhD work with John McLennan at Cambridge, which he finished at 2018, I believe. And he went from there to Maryland to work on a postdoc with Megan Newcomb, and for 2 years. And since 2021, he's with Terry Planck at Lamont, and he'll be talking today about the dichotomous nature of magnesium in plagioclase partitioning implications for diffusion chronometry. Euan.
Okay, hello everyone. Thank you for the invitation. Okay, so hopefully you can see.
Yeah, you're okay.
A full screen now. There's a volcano and a clock exploding. Great. So yeah, I'm going to be talking about some recent work that I've been doing, mostly thinking about magnesium partitioning in plagioclase, which may have some important implications for estimating diffusion timescales, as well as understanding thermal histories in magmatic systems. So plagioclase is a mineral that's really close to my heart. I spent a bit of time thinking about it, but it's also a really important mineral that igneous petrologists can use to understand changing magmatic conditions, as well as magmatic processes like magma storage, magma mixing, degassing, even magma ascent. And it's really important because it's stable in a wide range of magmatic compositions and systems, ranging from basalts all the way up to rhyolites. So it's kind of an important mineral at a range of tectonic settings. And so here we have this beautiful photomicrograph of a plagioclase that has this nice oscillatory zoning. And the fact that this zoning is preserved even at kind of magmatic temperatures, because the diffusivity of sodium, silicon, calcium, aluminum exchange is really slow, even at high temperatures, means that this mineral really is a perfect archive for recording changes in pressure, temperature, melt composition. So we can really get like a nice history of this plagioclase's lifetime. And also the fact that this anorthite is really slow at moving, it can also be useful for constraining initial conditions in diffusion chronometry. And so trace elements in magnesium, they all have different diffusivities, and they're a lot faster than anorthite or calcium, aluminum, sodium, silicon exchange. And so it means we can obtain information about timescales of processes that occur on a range of timescales. And so in the case of magnesium, which we're really going to be focusing on here, this is one of the faster elements that diffuses in plagioclase, and it kind of actually has a similar diffusivity to, say, iron magnesium into diffusion in olivine. So this means it can be used to constrain timescales of processes on the order of days to maybe even years or decades before eruption. And so if we hop over to the felsic domain or more silicic systems, kind of diffusion of trace elements in plagioclase have really provided important constraints on, say, the reservoir assembly prior to large caldera-forming eruptions, such as this work by Tim Druitt and others, which looked at the Minoan eruption from Santorini. But also the discrepancy between diffusion timescales calculated using trace elements in plagioclase like magnesium and strontium, and also crystallization ages obtained by uranium series disequilibria, have provided kind of valuable insights into kind of the conditions of crystal storage. And so this discrepancy where the diffusion timescales are a lot shorter than the crystal ages has really been at the forefront of this idea that crystals are stored at colder conditions, maybe even near the solidus. So this idea of cold storage. And this is because diffusion is a thermally activated process, whereas radiometric decay just carries on regardless. And so this suggests that maybe crystals only spend small excursions at high temperature where diffusion is active. And so now if we jump over to the mafic systems and basalt land, which I've spent most of my time thinking about, trace element diffusion and plagioclase has also provided quite valuable insights into the timescales of magma mixing, magma ascent, a range of tectonic settings from mid-ocean ridge basalts all the way up to OIBs like Iceland and so here's an example from a work by Fidel Costa in 2010 looking at the specific rise. But also magnesium diffusion and plagioclase can also be useful for constraining cooling rates in plutonic rocks, particularly when it's combined with partitioning between CPX and plage, which is temperature dependent. And so it has provided kind of valuable constraints on understanding the mechanisms of cooling, certainly in the lower oceanic crust. And whether, I guess it's still kind of controversial and highly debated whether it's conductive cooling or via hydrothermal systems, but magnesium diffusion and plagioclase has provided valuable constraints for this problem. And so another kind of useful thing is that now if, we're starting to see kind of timescale agreements and consistencies between diffusion timescales calculated using elements in olivine like iron magnesium interdiffusion, nickel and manganese, as well as magnesium diffusion and plagioclase, particularly in eruptions that show really good petrological and textural evidence to suggest that they've undergone a similar or the same magmatic history. So here's an example of an eruption I've worked on in Iceland called Skugafjall. And so we have this really beautiful chem scan image on the left, where there's these big blue plagioclases, olivine is in this kind of khaki green color, and CPX is in green. And the glass is in orange. And so what you can see is that you might be able to vaguely see the zoning in the olivine, not where the two minerals are in contact, but also nice zoning in plagioclase. And so if we look at the timescale distributions from these two mineral phases, we can actually see this remarkable consistency, regardless of the diffusion coefficient for magnesium and plagioclase that we use. So up here is we use the Facketal diffusion coefficient, and down here is Van Orman. So that we get a nice overlap between these different kernel density estimates. And so, yeah, this kind of highlights the importance of magnesium diffusion and plagioclase as a chronometer, and also the fact that plage is stable in a much wider range of compositions than olivine makes it kind of one of these really important chronometers that we need to be using. So here's like a brief primer on diffusion chronometry. I didn't want to spend too much time on this, but the way the method works is you have some zoning in a mineral, and diffusion will try to smooth out this compositional zoning through time. And so what often people do once this GIF starts going back around again is they start off with a step-like function, then they model the diffusion using some variant of Fick's second law through time. And often people end up with this nice kind of error function for the diffusion profile. Sorry about the ambulance, living in New York. But if we now look at diffusion and plagioclase, things are actually a little bit more complicated. So if you look at this video of a diffusion model from the Skugafjall eruption, we can see we don't have this nice error function. In fact, we have kind of a really complicated diffusion profile in the compositional domain. And in fact, the diffusion profile starts to mirror or reflect the anorthite profile. And this is because the diffusion of trace elements often is coupled with the anorthite content. There's usually a non-ideal interaction between the magnesium component and the anorthite or albite component. And so to kind of tackle this, we have to like modify the diffusion equation or Fick's second law. And so this is what Fidel, Costa, and others did back in 2003. And so what they had to incorporate was this A parameter, which basically is a thermodynamic parameter that describes this kind of non-ideal interaction between the trace elements and the anorthite components. But also there's additional complexities in plagioclase relating to its underlying structure. And this mostly relates to how aluminium is ordered within the structure. And so according to kind of Lowenstein's principle, the aluminium doesn't like to be next to other aluminiums. It wants to avoid other aluminiums in the structure at all costs. And so for one end member, say like albite, where we have a formula of 1 aluminium to 3 silicons in the tetrahedral sites, there's a lot more kind of configurations in which you can place aluminium within the structure. And so this is what we call a disordered structure, or what we call C1 bar. And then in the case of anorthite, we have 2 aluminiums to 2 silicon. And so actually the number of configurations we can put aluminium in is much more limited. We can only really put in these chains of aluminium, silicon, aluminium, silicon. So this is what we describe as an ordered structure, or we call this I1 bar. And so in this phase diagram, we can see that this transition between on this phase diagram from Carpenter and McConnell, you see this phase transition is temperature dependent. And this is because of entropy operating at higher temperatures. So at higher temperature, there's more entropy, and so there's more disorder in the structure. And so going across this transition, there's changes in, say, thermodynamic properties like the enthalpy of mixing, and also potentially some physical properties, which we'll discuss later. Okay, so we want to know this A parameter to be able to get the understand what the diffusion profile is going to look like, what the equilibrium profile is going to drive towards. And so people have often linked this A parameter to the partition coefficient between magnesium and melt, and how this depends on the anorthite content. However, we still don't really know very much about this, and it's really still quite hotly contested. And so some early empirical models, particularly that by Ilya Binderman and others, who did some experiments at kind of basaltic and basaltic andesitic conditions at high temperatures, generally found this kind of negative dependence between the anorthite content and the partition coefficient. And there's been some other models that have kind of shown similar things, but these are mostly based on kind of basalts. And then more recently, there's been a thermodynamic model, well, that incorporates a lattice strain component by Ralph Doman and John Blundy. And importantly, this model incorporates the effects of melt composition as well as temperature. But interestingly, what they found was actually the opposite sense, where the dependence on anorthite content has a positive relationship. And so this was one thing that really kind of was confusing as a PhD student. It was like, which model do we use? Because this will have a really important implication for the diffusion timescales we obtain, as well as interpreting what diffusion profiles in plagioclase actually mean. Are things close to equilibrium, or are things far from equilibrium? So this kind of conflict really needs to be resolved. And so maybe we can turn to nature, and that might reveal the answer. And certainly there's been a lot of studies done in kind of basaltic systems. And what they also started to see was also this kind of negative relationship between the anorthite content and magnesium and plagioclase. And so here's this example from Costa et al. Again. And what you can see is the magnesium content kind of nicely mirrors the anorthite profile. And interestingly, in this instance, the magnesium profile actually fits the equilibrium condition calculated using the Binderman model extremely well. And these are actually in crystals that are quite blocky. They look like they're quite texturally mature, and so maybe have potentially been stored in a hot environment for a long period of time and may have equilibrated. So yeah, there's this conflict between empirical observations we've made in basaltic systems, this lattice strain model. So which way do we go? Well, what does it all mean? Okay, so what we did was we compiled a new database of about 904 magnesium-in-plagioclase rim and glass pairs from experiments as well as carefully selected natural samples. We were mostly interested just in purely natural data, so we ended up kind of eliminating some experiments shown by these red dots that resided outside this kind of 99% georock quantile for the sodium and calcium contents of the liquid. So this ended up removing some experiments done at lower number of components, and also generally things that were pure anorthite. But most of our kind of data shown by the blue spots kind of covers a nice compositional range from basalts to rhyolites. There's some kind of alkalic things in there as well, but not that many. Okay, so now we plot up our partitioning data set. Initially, it doesn't look very remarkable. There's a lot of scatter and a lot of, maybe if you like squinted, you maybe say, maybe there's a negative dependence. But as kind of Doman and Blundy showed, that melt composition is really important. Certainly, say, for example, the silica content of the melts. So now when we plot up or color code based on silica content of the melt, we can actually see some trends emerge. So we can see different subparallel arrays corresponding to different liquid compositions. But perhaps interestingly, which kind of emerged was maybe we can potentially see some kinds of an inflection in this behavior. And so now if I overlay where the underlying structure changes, maybe this inflection point corresponds quite nicely to this. So what we did was we developed a new empirical model using segmented regression that also accounts for the liquid composition or the silica content of the liquid as well as temperature. And so if I plot up these some model curves from our model, it kind of starts to highlight potentially this change in behavior quite nicely. So you can see the position of this transition will change depending on the temperature. But yeah, we can generally see this nice, potentially this inflection or this change in behavior. Oops. So the way we developed this empirical model is, first of all, we had to parameterize, well, we used the parameterization of the C1 bar, I1 bar transition with temperature based on this Carpenter and McConnell model or parameterization. We then recast all of our data in our data set relative to this. So we calculated this parameter called X anorthite deviation. So, but what this basically means is that crystal zones in the C1 bar domain is going to have a negative value, and then things in the I1 bar domain is going to have a positive value, and things exactly at the transition is going to be 0. So then we fit our segmented regression through the data, and we fixed our breakpoints, or where the inflection occurs, at 0, so where this transition occurs. And so here's the kind of the formulation of the expression with the account for silica content as well as temperature. And on the right here, we have just showing the trade-offs between these different parameters. So I guess the important thing in this equation that we really want to consider is this term here, which is effectively the kind of this A parameter. And so what this means is this A parameter is positive in the C1 bar domain and negative in the I1 bar domain. So what about other cations or other divalent cations? And so here's another figure from Doman and Blundy, where they also show strontium and barium. But these elements don't really show this crazy flip in behavior. I mean, even in this figure, you might potentially see some change. But So why would this be the case? So if we're considering partitioning, then obviously we need to consider atomic or cation radius. And so we first consider strontium, barium. These are considerably bigger than or closer in size to cations associated with the M site, such as calcium and sodium. We also have things sat in the tetrahedral sites, so aluminium and silica, which have a much smaller cation radius. Whereas magnesium is quite interesting in the sense that it's smaller than strontium and barium, but it's very similar in size to both calcium, sodium, as well as things in the tetrahedral sites. And so what this means is that strontium and barium can only really partition into the M site in plagioclase, whereas the smaller size of magnesium means it has the potential to sit in both the M site as well as the T site. And I mean, this is not new or revolutionary. We've kind of known this for a long time, and people have proposed different reactions for these substitutions. So here's an example for the M site. Here's an example for the T site. And people have also proposed that maybe magnesium can diffuse through the tetrahedral framework in plagioclase. And this might be why there's an activity of silica dependence based on the Fack et al. Model. But another important thing to raise is that this lattice strain model of Doman and Blundy, it only assumes that magnesium sits in the M site. And so why might there be this kind of crazy change in behavior associated with magnesium? And one potential explanation could be that maybe site preference changes across this transition. And this could relate to changes in the size of the site, so the lengths of oxygen bonds. And so here's a figure from a Ross Angel paper from 1990, and it looks at kind of the length of tetrahedral oxygen bonds. The triangles are C1 bar domain plagioclases, the squares are I1 bar. And so what potentially might be happening is we have a significant change in the size of tetrahedral sites that may mean, or as well as M sites, that means that maybe magnesium may prefer to sit in, say, the T site at higher northite contents, whereas prefers to sit in the M sites maybe at lower northite contents. Obviously, a lot more work needs to be done exploring this effect, but this is maybe possibly one explanation. Maybe a change in site size maybe changes the preference in which magnesium goes to. So yeah, we quickly compare our model to previous examples. So the black dotted line is the model of Binderman et al. And the dashed lines are Doman and Blundy, and the solid lines are our model, all at different silica contents and temperatures. And so what we're generally finding is that our model is quite consistent with that of Doman and Blundy, particularly within the C1 bar domain, so within kind of five natural log units. And this is because both our models can account for this melt compositional effect. And there's good agreement, certainly within the C1 bar domain, because the slopes are quite similar. There's a positive slope, whereas we get significant deviation away from these two models at higher northite contents due to the change in slope. Likewise, for the Binderman model shown down here, we get good agreement with Binderman, where kind of their models were kind of calibrated at kind of in basaltic kind of systems, but then we get significant deviations away from that at different melt compositions, because their model doesn't really account for melt composition. So now we actually jump over to looking at natural crystals, or natural systems that weren't included in our calibration, and kind of some interesting things start to emerge. So we chose some samples from silicic systems like Toba, Serrigolan, Santorini, as well as intermediate systems like Krakatoa, and mafic systems like Wolf Volcano and Fernandina from the Galapagos. And so the interesting thing is, in a lot of kind of silicic systems, we often see this kind of positive correlation between anorthite content and magnesium. In kind of basaltic systems, generally we start seeing kind of negative correlations. But the really cool thing that kind of blew my mind is in these kind of transitional systems where we have a range of anorthite contents, we actually see this kind of flip in behavior. So this is quite prominent in Krakatoa as well as Santorini. And this is actually present in single crystals, single profiles, which are shown by these blue dots. And so if we add our some model curves to this data, all these curves are calculated using slightly different magnesium contents in the liquid, and we assumed a temperature and a silica content of the liquid. We can actually see that potentially some of these curves kind of agree quite well with the data. There's not perfect because these curves kind of assume there's equilibrium. And obviously there's going to be disequilibrium in natural systems that cause things to deviate away from these curves. But it's kind of quite interesting to see that our model curves agree quite well with some of the natural data. Even in, say, this Fernandina sample, which has some very evolved plagias, and there's potential evidence to suggest that these have equilibrated, we kind of potentially see this flip in behavior. Okay, so now let's just jump over to Krakatoa and take a closer look at this distribution, because I'm sure some people will be thinking, well, maybe fractional crystallization or crystallization can produce these this kind of kink in behavior rather than, say, diffusive reequilibration governed by the partitioning coefficients. And so what we did was we ran some isobaric fractional crystallization models. I'm just going to show the one from 1 kilobar, but we also ran one at 5 kilobars, which kind of gave the same results using rhyolite melts and a basaltic starting material. And so this also gave us another opportunity to actually compare different partitioning models as well. So we used these different partitioning models, calculated what the plage composition would be in equilibrium with these different melts. And so we can see just these fractional crystallization curves on the right here. So the red is Doman and Blundy, the purple is Binderman, and the blue is our model. And so what we can initially see is that the kind of the Doman and Blundy model and our model kind of fit this population at low anorthite contents generally quite well. The Binderman model doesn't really fit the data particularly well, and this could be due to the fact it can't account for this melt composition effect. And then at higher anorthite contents, the models just don't really fit the data super well. Maybe in this instance, our model fits this high anorthite population quite well, but this high anorthite, low magnesium population that the models fail to fit. So this suggests that maybe fractional crystallization alone cannot create the kind of magnesium distributions observed in this plagioclase population. So okay, well, now let's consider the effect of diffusive reequilibration combined with crystallization. So let's say these high anorthite plagias, they were stored and they diffusively reequilibrated. And so their distributions would be governed by the partitioning relationship. And so we assume they kind of reequilibrated with a composition around here. And so what we find is that our model fits this distribution really well. The Doman and Blundy model fails to fit this distribution because the slope is the wrong sign. And finally, the Binderman model it has the correct shape, but maybe not, but it's kind of displaced downwards. So what this kind of change, this odd like kinked partitioning relationship may have some important implications for kind of the shapes of equilibrium profiles. And so what we did was we ran some theoretical models or simplified models with 2 or 3 zones, a rim and a core in between. And we just looked at how like different compositions or anorthite compositions would affect the shape of the equilibrium profile. So in this instance, we have 2 zones on this kind of in the C1 bar domain. And so what this would produce is a equilibrium profile that's shaped like this. So there's a positive correlation between anorthite content and magnesium. Then if we look at say a basaltic plagioclase, which is sitting on the other side in the I1 bar domain, we start off from the same initial conditions. We end up with an equilibrium profile where there's an anti-correlation between the anorthite content and the magnesium content. Whereas one really interesting thing potentially would be if we had a situation where the anorthite zones were perfectly exactly on either side of this transition, then we could actually end up with a flat equilibrium profile. And then finally, also, we could still, if we still had compositions on either side of this transition, then potentially the shape would be governed by like the slope between these different points. And so finally, so this will have like a really important implications for understanding the shapes and of equilibrium profiles and what they may mean. And so this may be particularly true for silicic systems, where we see this complete change in sign that people have in the partitioning relationship that people have traditionally used. And so here's some examples that a student from Oregon State, Jordan Lubbers, was looking at. So he was looking at some crystals from some plage crystals from Toba and Cerro Golan, and he found some kind of quite confusing features, I guess. So he had strontium profiles that were quite close to a calculated equilibrium condition calculated using the Binderman model, whereas his magnesium profiles were really far away from equilibrium. So they potentially would be considered there's significant disequilibrium. But this could be considered maybe a bit confusing because magnesium's significantly faster diffuser than strontium. It's potentially 40 times faster. So you would expect potentially magnesium to also show or be equilibrated if strontium's close to being equilibrated. So now if we just consider, if we use our partitioning model, which has the opposite slope in the C1 bar domain, we can see that the data fits this equilibrium condition super well. And so what this could actually suggest is that, yeah, in this instance, magnesium also equilibrated. The strontium is kind of close to equilibrium, but hasn't quite got there. And so, yeah, just to summarize, so yeah, I think we find that potentially the plagioclase structure can influence the magnesium partitioning behavior. We see potentially a major inflection in partitioning behavior that could correspond to this C1 bar, I1 bar transition. And so we've developed a new empirical model using a segmented regression that could account for this behavior as well as the effects of temperature and melt composition. And so our model can actually fit some magnesium composition distributions observed in natural crystals fairly well. So yeah, this kind of really have some significant implications for how we interpret diffusion profiles in certainly silicic systems. Things that may be close to or show significant disequilibrium may in fact be close to equilibrium and vice versa. So yeah, this could be really important for understanding not just diffusion timescales, but also kind of thermal states and magmatic histories at a range of tectonic settings. And so, yeah, I'll leave it there. I'll be really keen to hear questions and feedback. And if you have other feedback, feel free to email me at this address down here. Thank you.
Thank you, Euan. That's a very nice summary again from using diffusion modeling, giving some background, and then going on to using crystallography with it. So whatever the discussion on this one, I'm very pleased to see that trace element and crystallography is being tied up finally, because I've been arguing for that case for a long time, and it's good to see someone doing that. So questions to Euan. So I'm getting some comments on chat. Jim Van Orman says nice work, but if you have questions, you can either unmute yourself and say something or put in the chat, Ralph.
Yeah, so I don't have a real question. So congratulations, I think it's great work, and I'm now really hoping that we made a large step in solving this problem with this thermodynamic factor for magnesium. I mean, and you're right, we did not consider in the model of Domen-Blandy that magnesium could sit on the T side. That's a possible explanation, of course, of your trends. I'm not sure, Shumit, do you know, so Carty-Fark's experiment, so there's a paper of Fark et al. Who looked at the partitioning of magnesium between clinopyroxene and plagioclase, also for different plagioclase compositions. There she found also a similar trend as predicted by Domen-Blandy model. I don't remember if these plagioclases are in the I1 bar or C1 bar stability field. Do you know that?
Yeah, they're in the mix. I was looking at the diagram as we were showing it, and this was right where it becomes dependent on temperature and composition and things. But one of the things that so I was going to ask this later or say this later was an added twist that comes to this is that one of the implications from the Fark et al. Data was that magnesium actually partitions between both as well. So it's not either or. It doesn't go either to the M side or to the T side. It actually partitions partly between the two. So that's an added level of twist that needs to come in at some point. But
I agree. I mean, I kind of simplified. But I suspect, it does sit in both, but maybe there's more of a preference, on one side versus another.
I mean, you got to do that at the first cut, of course, but so that's one of the, from the experimental data, that's what it looked like, that you couldn't explain all of the observations by putting magnesium either on one side or the other side. So that's the next level to go to. But Garrett, you have a question?
Hi, I never quite got my plagioclase to really fit with the Binderman model. So it looks like you used some of mine in your paper, and it looks like you got a good fit. I just wanted to know whether because I did some diffusion modeling with those crystals. Do you have any idea how using your model would change the timescales I got from those plagioclase?
I don't know. I mean, I guess we'd have to see. I mean, it might also affect like the shape of the initial condition, because I think in your paper you used and the relationships between strontium and anorthite, and related that to the magnesium content.
I think
so it might affect it in that way. But I don't know. I don't know how it would have possibly affect the time. But
so there's no quick relationship between it. So but I guess you would have to change the initial conditions and the diffusion modeling itself took into account the coefficients.
Yeah, exactly. Because there's also this melt composition effect that Ralph and John found, which would affect if the silica content of the liquids you're exploring also changes. That's going to shift everything up or down. But I think it's quite exciting. I think it was actually your data set that made me think whoa, maybe we do see this in natural systems, and I was kind of trying to convince myself it's a real thing, and I spent a long time thinking about this. It was only really when I came across Amber's Krakatoa data where it was really prominent. Because I've been racking my head over ages being we see it negative in basalt, but the Domen-Blandy model suggests opposite, and so maybe this is a good thing that can reconcile these different observations.
I mean, again, just makes a strong case against that we need to worry about crystallography.
Yeah, exactly. Yeah.
So So I have a question for you on the chat from Ephraim, who's saying, good presentation. Question is, can you model also be used for silica undersaturated magma? If I'm not wrong, I saw in one of your slides that you used only rocks from 45% SiO2.
Yeah, I mean, obviously, like any model, I guess you have to kind of stick to kind of the calibration range. Often when people like try, if they were interested in, say, in diffusion modeling, and you assume that, say, I mean, it's obviously a big assumption, but you know, often you assume the temperature's fixed, the liquid composition outside the crystal's fixed, then a lot of these like extra terms, like the silica content and the temperature, often you don't need to use, and it's just the A parameter that's really important in fixing the shape of the profile. But yeah, if it's more important for like, if you wanted to estimate the magnesium content in the plage for a given liquid composition, then yeah, I'd probably suggest, yeah, trying to stick to the calibrated range, but I don't know, maybe others in here have an opinion.
Does somebody have thoughts on it? Ralph, yeah.
Yeah, so I think there's a paper of Miller et al. In 2006 or so, where
2006.
they looked at the effect of melting partition of magnesium between T side and for pure anorthite. Do you hear me now?
Yeah, I can hear you. Sorry, yeah.
It's a little choppy, but we hear you.
Can you hear me? Yeah, sorry about this. Just the moment was fine before, but it's better now.
Yeah.
Yeah.
Okay. So I'm saying that again. So there's a paper of Miller et al. In 2006 where they looked at the effect of melt composition on the partition between pure anorthite and melt, and the effect and also the distribution between the two sites. And they saw, I think, an effect of the melt composition. So silica content also potentially then affects the partitioning of magnesium between the two sites. Yeah, I don't know if that, yeah, how significant that is. I don't know, remember really.
Yeah, I remember we used that in the Fachetal paper, and that's a CMAS melt though. So if you have a more complex melt, the effect could be bigger if you move away from CMAS. And yeah, so they did see some effect there. That comes in as a non-ideality on the melt. Okay, so Hadi Umrani has a question that, would you please explain what is the role of mineral paragenesis on your model, diffusion of Mg-in-plagioclase, olivine CPX, or oxygen fugacity? So basically, whether the assemblage has a role to play on the whole thing.
I don't think it will, or I mean, yeah, I don't think it should if it's just looking at the silica content of the liquids. But yeah, likewise for oxygen fugacity, we didn't include that in the calibration, because I mean, certainly in like some of the natural samples, it's hard to get like a good constraint on FO2. And yeah, I think maybe in an experimental case, maybe people need to like actually try and measure like Fe3+ in the mineral structure rather than inferring from FO2. And also like things like water content, we didn't really fully account for that. I mean, it's kind of maybe wrapped up a little bit in the anorthite term, because that is affected by water, but
thermodynamically, it will be anything that affects the activity of silica through a non-ideality term would affect it. So that's the question to ask, whether whatever in oxygen fugacity or some other concentration will affect the activity of silica, because that's what's controlling the partition.
Yeah.
Now, going to your equation, I had a question as well. So your empirical fit is obviously an empirical function, but I saw there was a square of temperature in it. How big a role does it play? Because the reason I'm asking that is because adding a square of temperature has a different thermodynamic significance. It can really, if it is a big role, it can really throw things off when you extrapolate.
Yeah. So, well, in this instance, we kind of added a square because we're kind of following like Ralph's formulation, I guess. But it's not huge. I mean, we also did like a fit, like a linear fit as well, that I can actually probably include in the supplement of the paper, but it's not a huge effect,
Okay.
or at least it's not a huge squared effect, I think.
Yeah, so sorry, just to interrupt. So it's our formulation is of course derived from thermodynamics. So I do not remember how then we got a T square dependence. But
well, it would imply a heat dependence on heat capacity. That's how you would, because oxygen, oxygen isotopes and things depend on T squared, and elements usually are 1/T because the heat capacity is not temperature dependent. But Jim, did you have something to say? Or?
I was just going to add, it looked like in your correlation diagrams that those two parameters were highly correlated. So I wondered if you could just simplify it a bit.
Yeah, I think ultimately, yeah, it was one of those things where when I was doing it, I was like, well, I'll try and follow this like this way, but I also did it like multiple ways, and so maybe yeah, it could just be simple linear fit.
Mm-hmm. Okay, so now I'd just like to remind people we can ask questions to Massimo as well, and so either to Euan or to Massimo. And going back to Massimo's talk, what I wanted to mention was that seemed like speed is, of course, a key thing for doing petrological monitoring. And with diffusion chronometry, what's becoming very useful is the use of image analysis to get to models, profiles, and maps and things instead of measuring profiles, which obviously take a lot of time. So that may be a way where a lot of development may be coming in the future to speed up diffusion chronometry and make it more useful for monitoring studies. So any other questions, comments?
I agree with this. Sumit, I agree with this. So if there is any new improvement for the point of view of speediness, I know now, for example, the detector for the X-ray mapping is very large, so you can do also maps in a few minutes without problem. So I agree with you.
Yeah, so that'd be exciting to to do these things in real time. It's beginning to be done, but it'd be very useful. Rosa, yeah, please. Go ahead.
Hi. So I have a question about plagioclase actually, because I have been working on plagioclase during my PhD in Montserrat Island, and I was doing some modelings, and I want to share with you my experience because also I try to use both partition coefficients, and I'm also posting in supplementary data. You can find both. And actually it was a bit complicated for me because at Soufriere Hills you have mixing between enclaves and hosts, so basaltic andesite and andesite. And plagioclase were also migrated, and because you have disaggregation with enclaves into hosts, so basically it was hard for me to use the partition coefficient from Dohm and Blandy, because you need to know the silica content, right? And so sometimes it was changing because the plagioclase were recalibrating in the enclave, sometimes in the host. And so it was difficult to tracking. And it was crazy I found something like, sometimes I had like a high anortile content, like 80, but the temperature, it was low, so it was in equilibrium with the low temperature. So, I mean, for me, it was a bit confusing to use that. And so I went through Biedermann, and it was working. I found some rings in equilibrium with the melt, and so I used that one. So I was just sharing this experience. It was complicated, but at the end, I just focused on the Biedermann. And the only problem that I found, it was sometimes to find, how can I say, realistic correlation between the anorthite content and the temperature that it was in equilibrium that melt in the magnesium that I calculated. So I don't know if it was just a bit difficult, but at the end I went through.
Thoughts on that, anybody?
I was just, and it was interesting anyway. And then I used a diffusion coefficient from Van Orman 2014 as well. And anyway, it was nice today to talk about this and share also your experience. Thank you so for this.
Yeah, I mean, I completely agree. As someone who is like tried thinking about plagioclase, and yeah, I mean, I did say in my talk, oh, it's a great chronometer, and you know, it's powerful in the sense that it's got a large composite, like can be used in a large compositional range. But yeah, the issue is that it's a little bit more complicated than, say, I mean, I guess diffusion chronometry is complicated in every mineral, but this kind of partitioning business makes plag even a little bit more complicated.
And I think you make a very important point that the partition coefficient is one part of it, but then also to just know what composition it was actually equilibrating with. That's always a very tricky part of this whole thing. So if you go back to that Costa et al. 2010 paper, that's where, you know, it was quite surprising that the actual melt we ended up modeling it was quite a bit more primitive than anything that was seen around there. And so, yeah, but it is always a challenge, and the kinds of rocks you're describing, yeah, it would be quite difficult to decide what to use there. And as you said, you know, depending on what you use, you get quite different results. So that's something should be. So one of the hopes is that if you use multiple trace elements on the same sample, that could help you narrow down the kind of compositions you're using. Any other thoughts or questions? I have to get rid of it. Let me see if I can. Oops. I don't want to hit the wrong button. It's telling me to close the meeting, which I don't want to do yet. But I want to see the chat. Don't see anything in the chat there. So.
Yeah, I have one more.
Yeah, go ahead, Ralph.
Comment or question. Yeah, it would be interesting if you do the same approach for strontium or barium, because there you would not expect this kink related to the C1 by I1 bar transition, because they should not go to the T side. So that would be a nice test also.
Yeah, I think at least like looking at your data set, it didn't look like there was a huge change. I mean, there might have. I mean, I tried speaking to Michael Carpenter, who's he's like a plag mineralogist at Cambridge, and he was like, "Oh, you probably expect like maybe a small change across the transition, but even for like, say, strontium and barium, I guess maybe the overall like direction of the slope will be the same, but maybe there'll be a small change, but it won't be like completely the opposite. It won't go from positive to negative, or
I mean, they also have a stronger dependence. So, you know, magnesium, it's basically close to zero. So it goes a little positive or a little negative, and makes it trickier.
Yeah, exactly. But it kind of, I also wonder whether if there is, whether the fact that you could, it does potentially sit in different sites. It also maybe explains the difference in the kind of the two diffusion coefficients, and that explains behavior maybe, because I seem to remember like, yeah, Kathy found no anisotropy, as James found some, whether that's, yeah, depending on where it sits, depends on its diffusion.
Yeah, and there's a role of silica activity that needs to be sorted out on that one.
Yeah, exactly. But at least for like the eruption I looked at in Iceland, yeah, they kind of nicely agree with the olivine timescales, and even I think the recent Fagradalsfjall eruption that Marin's been working on, we kind of see a nice agreement between these two minerals as well. I mean, in diffusion chronometry land, where the uncertainties are generally quite large anyway, but
yeah, within the uncertainty, if it comes out close, that's always a reassuring thing to see. So
yeah.
I don't see any other questions or comments coming up. So I'll give a last call here for anyone who has something on their minds to discuss or question. If not, thank Massimo and Euan again for two very nice talks and a lot of food to think about. To all of you here, the talks will be on the website in a couple of days. They're recorded. So if you want to go back and refresh your memory on what you heard, because they're nice review components, both of the talks on various aspects, so you can do that. And with that, I'd like to just repeat again that we'll go on a summer break, so there'll be no talks in the next couple of months. And we'll be back around September or October, and we'll send out mails to let you know ahead of time when we're doing that. So on that note, I'll wish all of you a happy summer holidays and catch up with you later. Thank you. Bye-bye.